So this event today has two different sides. First of all, we're welcoming our international guests who are participating in the Planetary Defence Conference this week here in Vienna. My name is Christian Korbel. I'm a professor at the University of Vienna and also chair of the Geosciences Committee of the Academy of Sciences, which is hosting us today. And the second reason for today's event is to inform also the public a little bit about what's going on. In this respect, I have a question. I'll be switching to German here for a moment. So, sehr geehrte Damen und Herren, jene unter Ihnen, die diesen Event hier nicht als wissenschaftlicher Sicht, sondern einfach zur Information haben, für Sie habe ich eine Frage. Wir haben 3 der Vorträge jedenfalls auf Englisch, so ist es auch angekündigt. Mein Vortrag selbst, das ist der erste, kann sowohl auf Deutsch wie auch auf Englisch stattfinden. Und der letzte Vortrag von Herrn Dr. Küppers von der ESA kann auch Deutsch oder Englisch stattfinden. Die Frage ist jetzt, wir haben hier ein sehr stark internationales Publikum und daher ist es vielleicht leicht besser, wenn wir die Vorträge auf Englisch halten könnten. Wenn es aber unter Ihnen jemanden gibt, der absolut nicht Englisch, es sind hauptsächlich Bilder, versteht, dann bitte aufzeigen. Ich sehe niemanden. So, now I can switch back to English. I was asking a possible German speaker if they absolutely do not understand any English, and most of the slides, there's lots of slides anyway, so, and I didn't see any hands up that we have to do the talks in German. I think we'll just, for our international public, and also the event is being recorded and will later be available online, we can just maybe speak not too fast. So I have to remind myself of doing that too. Anyway, so I already said a hearty welcome today from the Austrian Academy of Sciences. The Austrian Academy has a number of committees and members. There are members. It's a learned society, similar in the US, the National Academy, for example, and many other countries, Leopoldina in Germany and so on, have scientists who are members. I'm a full member of the Academy, and as such, I'm also heading the Geosciences Committee. I'm also deputy head of the Astronomy Committee of the Academy, and in that capacity, we were able to invite you here today to have this event. The Academy of Sciences is, as I said, a learned society. It is unusually for some academies both a research institution and a learned society. So we have members who are scientists who are meeting for lectures, public outreach, and so on and so forth, but our academy also has institutes that do scientific research. We are one of the largest non-university research organizations in Austria, and there are scientific research institutes that range in topic from Iranian studies on the one hand and theater studies to space sciences, material sciences, high energy physics, and a variety of other topics. We have about 1,000 scientists and associated researchers who are employed by the Academy. The Academy has recently celebrated its 175th anniversary. Since 1850 approximately, the Academy has been in this building. This building, however, is about 100-something years older than that because it used to be the central building of the University of Vienna that had been moving around a little bit. The University of Vienna, however, is relatively old. It was founded in 1365 and is the oldest still existing and operating German language university in the world. University of Vienna has about currently 90,000 students and about 10,000 staff. So you can see kind of this was the main building of the university before it became the main building of the academy, and related to that we have buildings nearby that also are occupied by academy, institutes, and scientists and organizations. So that's all I wanted to say about the introduction. Now we have, as I said, 5 lectures. It starts with my own lecture where I give a very brief overview of impacts, mainly on the Earth. This is the stuff that I do as a researcher at the University of Vienna, kind of the day job. The next presentation will be by Lindley Johnson about planetary defense at NASA. Then we have Lena Adams from Johns Hopkins about the DART mission. And then Nancy Chabot talking about the post-impact aspect of the DART mission. She's also from Johns Hopkins. And then Michael Küppers from ESA about the next step, which is the Hera mission. After each talk, which is going to last about maybe 20 minutes, something like that, we have a chance to have a few questions. So I'll take the questions. I'll moderate the event this afternoon. And after we're done with that, and the sooner we're done, we can all go downstairs and have all kinds of refreshments and maybe a few snacks as well, courtesy of the Academy, supported, by the way, I have to say, by the Austrian Space Forum as well. So with that, I'll start with my own presentation here. We'll see that I at least stay in time. We started about 5 minutes late because we were trying to give people a chance in this bad weather to come in. Now, what I wanted to talk about, and my first slide is in both languages because I was not sure which of the two I'll be going with. So I'm going to talk a little bit about impacts. First, a few slides about how they look like in various places of the solar system, but mainly, how do we find impacts on Earth? How do we identify them? And what does that all mean? So, the next slide is an object that we all know very well, our closest neighbor in space, the Moon. And it has, as you know, lots of craters on the surface and big impact basins as well that are the mare. Now this is something, of course, that was not knowledge for hundreds of years, that was only slowly figured out with time, and we really only have the confirmation that these craters on the Moon are of impact origin more or less since the first missions to the Moon that happened on the order of 50 years ago. Now, the craters on the Moon, as we know now, but people didn't know back then when they were discovered in the 17th century, when they thought they were volcanic, but now we know they're all of impact origin. And it is a sobering thought, in a way, to think that our Earth would look the same way if we did not have active geological processes going on the surface of the Earth that obscure, cover up, or obliterate the traces of impacts on the Earth. But that also tells us that impacts form on the surface of the Earth, of course, with approximately the same frequency. So how often per century or millennium or whatever do impacts happen? Well, they happen on the Moon actually a little bit less often than they do on the Earth, because the Earth has a greater gravitational attraction. So this is something to keep in mind. But before we come to the Earth, I want to show a few pictures of other places in the solar system. On the upper left, we have the surface of Mercury. And of course, if you're not a planetary scientist, you know, some people might think, oh, this is the Moon, but it's not. It's the innermost planet, Mercury, and this is a mosaic from one of the spacecraft that went there a while ago, and it shows that the surface is covered by craters. Mercury, just like the Moon, does not really have any type of atmosphere, and also geological processes on the surface of Mercury or the Moon haven't operated for a long, long time, at least not to the extent They would on other planetary bodies. The image on the bottom shows a radar image of a crater on the surface of Venus, second planet, often called the sister planet of Earth. But it's kind of an interesting sister because even though the size is about the same, the surface is totally different. We can't even see it, of course, from the outside because it is covered with a very dense atmosphere that is about 100 times denser than the Earth's atmosphere and consists almost solely of carbon dioxide, 96% carbon dioxide, which also means that the surface temperature of Venus is close to 500 degrees Celsius. So it's a rather unpleasant place. And the clouds, by the way, in the atmosphere consist of sulfuric acid, so also not very habitable. And to see craters and other surface features, we need radar, and there have been a number of missions that have been doing that. And this image shows about a 30-kilometer diameter crater with the impact ejector beautifully visible. And of course, the dense atmosphere keeps them close to the crater, not like on the moon or on the Earth, where they would fly away much further. Then we have an image of the red planet Venus on the upper right. And also here we see a lot of craters. Mars does have an atmosphere, but it's about 5/100 of that of density of the Earth atmosphere, so not much retardation going on. But you can even observe fresh impact craters forming on the surface of Mars. Here, for example, is a small crater structure that was seen on an image taken in 2011 by a spacecraft around Mars, but was not present in an image taken 2 years earlier. So craters form, we see it on the moon too. Then here we have a few pictures of the culprits that make most of the impacts in the inner solar system, the asteroids. Those are some images of those that had been visited by spacecraft so far. And what we can see, something very interesting apart from the irregular shape, even of large asteroids, is that they themselves have the traces of collisions. They're covered by craters themselves. So we see that collisions in the solar system are something that happens all the time. We can also go to the outer solar system. The planets, of course, out there don't have solid surfaces. Jupiter, Saturn, Uranus, Neptune are known as the gas and ice giants, but their moons do have solid surfaces. And what we see here is a mixture of images from different moons, in this case of Jupiter and Saturn, that shows a lot of impact structures. Even the upper left image, Europa, has a surface, one of the moons of Jupiter has a surface that is a thick ice crust. Even there, where there's ice tectonics, we do see evidence for impact craters. So we basically see that impact craters are a predominant landform on all objects in our solar system that have solid surfaces. And they are predominant geological processes. Now, here's one of the German slides that I threw in. When we have an extraterrestrial object coming down onto the Earth, it depends a little bit on the size, what happens. We have an object that outside, which is a small asteroid, outside the Earth atmosphere would be called a meteoroid. So those are small asteroids. When it enters the Earth atmosphere and it starts to ionize the atmosphere, so what we see up there is not the object itself glowing, it is the atmosphere that through the heat from the fast movement of the object is made to glow. That's called a meteor. Small meteors you all know as shooting stars, for example, and the large ones, they would be called fireballs. And sometimes these objects that are slowed down, they move very fast, many kilometers per second outside the Earth atmosphere. Then they enter the Earth atmosphere, they're slowed down, and if there's something left over and doesn't burn up and fall down on the ground, it's called a meteorite. But it's always the same object. Outside the Earth atmosphere, a meteoroid. In the atmosphere, a meteor, and if it's on the ground, a meteorite. Might be confusing a little bit, but it has historical reasons. And if the object is large enough that it is not slowed down in the atmosphere, but hits the ground basically with more or less extraterrestrial velocities, several kilometers per second, then the middle case applies. We have a meteorite crater. And this is where we come to craters on the Earth. This is probably the most famous of all of them. This is called Meteor Crater. It is in northern Arizona, not too far, by the way, from the Grand Canyon. So if you ever go there, it's a nice thing to combine. It's also called Barringer Crater, after the first person who did detailed scientific investigations and drillings at this crater structure at the beginning of the 20th century. It's interesting to note that already in the late 19th century, meteorite fragments had been found scattered around the crater, but they were not really brought in conjunction with the crater, and people were thinking, well, this is a volcanic structure because nearby there are other really volcanic structures. And the meteorite itself is not named after this crater, which of course at that time wasn't called Meteor Crater, obviously, but it was called Coon Butte. Obviously lots of coons sunning themselves on the rim of this crater. But the meteorites were named after that tiny little canyon in the upper right of the image here, which is called Canyon Diablo. So if you find any Canyon Diablo meteorites, they are the ones there from this crater. And originally, the person who investigated this crater in more detail, Daniel Moreau Barringer, early in the 20th century, thought that this was made by a huge meteorite, and the meteorite is buried underneath the crater floor, and he's going to drill it up and get rich. Well, didn't quite happen that way for reasons that we now understand, but back then people didn't quite understand, and I'll come back to that later, which has to do with that the object that they originally thought would make such a crater was much larger than we now know is necessary. But before we talk about this in more detail, a few more images of other craters on Earth. On the upper left, one in Namibia, that's 2.5 kilometers in diameter. On the bottom one, Zwang in South Africa, 1.2 kilometers in diameter, which, by the way, is exactly the same size. Just remember that image here for a second and compare that with this one here. It's the same size. 1.2 kilometers in diameter. Now, why do they look so different? This is because this crater here is 50,000 years old approximately, and this crater on the bottom here is about 250,000 years old. And in between, Earth's geology has already taken action and eroded the crater rim down, filled in the crater interior, and you will not find at this crater at Zwang any evidence that this is an impact crater right at the surface. It actually required drill cores to get to the bottom, so to say, of it. And so this is the point. The other crater up there in Namibia is almost covered by sand, and it's only about 3-4 million years old. So what happens on Earth relatively quickly is that craters that on the moon would stick out immediately, this is clearly an impact crater. On the Earth, they're not so easy to recognize. Lona crater in India, one of the few craters on Earth in basaltic rock where we can learn something locally, directly about the impact response of basalts. Took a long time to be recognized as an impact crater as well. Many people thought it was a volcanic structure. This is an interesting case. This is Gosses Bluff in Australia. And I have listed it as 22 kilometers in diameter. And when you see this ring of hills that is also shown on the bottom right in an aerial photograph, you'd think that this is actually the crater or the crater rim, but this is actually not so. This is the deeply eroded remnant of a central peak of this crater, because larger craters, they have a central peak as well, not only a crater rim. The crater itself is long eroded, and the original crater rim is long gone. You just see this halo, this circular halo around around the central feature here that indicates the original extent of that crater. And this is interesting. This crater is about 140-something million years old. And compared to the age of the Earth, just 4.5 billion years, and all the craters on the moon that are also several billion years old, basically here you have a relatively not so old crater on the surface of the Earth, and it's already very difficult to see. It gets more interesting. Here is one that's a bit over 200 million years old in Canada, and you'd think that this is the crater that you see there. In fact, not. This is also the deeply eroded remnant of a central feature, and we only see that because Hydro-Quebec in Canada built a dam that made a reservoir there, and so we can see actually a circular feature. The original crater, which is about 2.5 times in diameter of the central feature, is not really visible on the surface anymore. Only detailed geological and geophysical methods reveal that. Here is another guessing example. Where is the crater? Well, we have in the middle a round feature, a little bit off center to the left. Let's see, does this work here? Yeah, here, this is the, here. This is this feature here, but this is just the central lake. The original crater is somewhere, or, oops, no, I don't know how this, oh, should I do that on here? No. Anyway, the original crater is somewhere around this thing with about 90, maybe 100, maybe 75 kilometers in diameter. We don't know exactly. This is a little over 500 million years old, so it's not all that old as things go on the Earth. Actually, this is the currently second oldest so far identified impact structure on the surface of the Earth, and the largest one that we have ever seen. Actually, it's not the impact structure itself, it is the deeply eroded remnant of what used to be the Fredefort impact structure, which is 2 billion years old. 2 billion years is not even half the age of our planet. So this is one of the oldest one that we have, and it's deeply eroded. We have lost from the surface about 10 kilometers down. Imagine 10 kilometers going down. So what we see here are rocks that used to be shortly after the impact 10 kilometers below the surface. So this is all that's left in this case, and any smaller structure would be completely obliterated and eroded away from the surface. So even so, it was possible over the decades to identify approximately currently, latest status, about 200 impact craters on the Earth's surface. Here is a map that shows approximately where most of them are, and you'll see there are none really, or just 2 on the ocean floor. Why? Because first, to form a crater on the ocean floor, well, you have to penetrate through to the ocean floor. Others make just a big splash and some tsunamis. And the other thing is the ocean floor is very young on the Earth's surface. There's no ocean floor that's younger or older than 200 million years, most of it much younger. And also it's not so easy to study. So there's a variety of reasons why most of them are on continents, and most of them that we see here are in places that have old terrestrial surface rocks. Australia, Southern Africa, Canada, the Baltic Shield, and so on. So this reflects both geological realities, but also where people are actually searching, active search programs. So I've mentioned that the oldest impact on Earth is the Fredefort, or one of the 2 oldest, the Fredefort, the largest one for sure. But the billion years after that, we also don't have very many craters on the Earth's surface, and before, nothing that is older than about 3.5 billion years, and from 3.5 to about 2.5 billion years, we have some scattered ejecta from craters, where the craters themselves are either long eroded or haven't been found yet, or are simply not preserved. And so we have still a wide open field of research. Therefore, if we want to know more about craters in the early solar system, it's a good idea to look at the moon or at other bodies in the solar system, because they haven't been subject to all these changes. So very briefly, how does an impact crater form? Well, a small object moves very, very fast and hits the surface of the Earth or the moon with very high velocity. We're talking about many kilometers per second, 10, 20, 30, 40 kilometers per second. Upon impact, the object is of course stopped, the kinetic energy is transferred into heat, melting the rocks, excavating the crater, and so on, and shocked rocks are formed through the shock wave that penetrates the rock, and then at the end we have a crater. This whole thing happens very, very fast, a few seconds, but maybe a few minutes for large crater structures. So it is one of the highest energy geological events and fastest geological events that we can imagine. Unfortunately, we haven't seen one on the surface of the Earth yet, and this is, of course, why we are here, to try and prevent that they cause any damage. How do we identify impact craters on the surface of the Earth? Well, I'll just go straight to the last parts, because just having a circular feature is not good enough. Any geophysical anomalies is not good enough, because there's many other geological processes that could cause similar type of effects. What is unique to impact is that we can find traces of what is called shock metamorphisms, or shocked rocks, and shocked minerals. I'll show a couple of images on that. And if there is any remnant of the extraterrestrial body that made the crater mixed in with predominantly terrestrial rocks. And so these two things are the only type of evidence that help us identify impact craters uniquely and without any doubt on the surface of the Earth. So here we have an example of a macroscopic shock feature, which is called a shatter cone. This object here is about 20-25 centimeters across, and you see these beautiful striations going down. That is formed in usually fine-grained rocks during impact. But let's be careful. The image on the lower left shows something that looks, for people who are not experts, kind of similar. Also striations, but they're actually sedimentary, so-called cone-in-cone features. If we go to the microscopic level, we take rocks like this. This is a suevite, for example, from a crater in Ghana in West Africa. A suevite is a breccia that is composed of different rock types thrown together. But in between that kind of yellowish, greenish type bubbly stuff that you see in there, those are actually remnants of glass. So here the rock has been melted as a response to the impact itself. And if we make microscopic sections of this rock and enlarge it very large, we might see features like this in there. Those are quartz grains. Quartz does not normally show these interesting striations in there, which are called planar deformation features. Those are responses of the crystal structure to high pressure shock, which then leads to these features that are formed in more than one set. One set is these parallel features, and then you have some that go into other directions, and this is what experts know how to recognize impacts on Earth, at least. And of course, you have the same response in meteorites, on lunar rocks, and so on and so forth. But no volcanic feature on Earth or anywhere else will show such an event. The other possibility is, and this is something that I do in my laboratory in Vienna a lot, we look at the extraterrestrial admixture, a little bit of the meteoritic component that is mixed in with predominantly terrestrial rocks. It's a little bit similar if when you make a big pot of soup and you put some salt in there, you will not see it, but there are ways how to find out how much salt is in there, in that pot. And the same thing about rocks. You don't see the extraterrestrial component, but there are. It's a little bit complicated, using platinum group element abundances in various ratios of some rare isotopes, such as the element osmium, but also the element chromium, that have typical fingerprints that tell us that there is a meteoritic component in there, and therefore they can only have formed by impact, not by volcanic melting and similar things. So we study impact craters on Earth because they are unique geological features. They allow us to ground truth, basically, impact processes elsewhere in the solar system by allowing us to study these things in 3D, basically. We can drill them, we can go to outcrops and so on, something that we can't normally do on other planets or moons. But it's not an easy topic, it needs some experience. Of course, we know one of the most prominent impacts that people have been talking about happened about 66 million years ago. The remnant of that is the boundary between the Cretaceous age rocks and the Tertiary age rocks, which has an extraterrestrial component and some shocked rocks in there. Used to be called the Cretaceous Tertiary boundary. Today it's called the Cretaceous Paleogene boundary. Geologists have just changed the name a little bit. But that thin layer in between, that has an extraterrestrial component. It took a long time, over 10 years after the extraterrestrial component was confirmed, that in fact the crater was identified as the Chicxulub impact structure in Mexico, approximately 200 kilometers in diameter, not visible on the surface of the Earth because later geological processes have covered it up. So it was basically covered with several hundred meters of younger rocks, so you don't see it on the surface, and therefore it took drilling and tracing back the ejecta before that crater was found. So this is what might have happened back then. And since we're in Vienna, I'll show you a little bit about what could happen here. This is meteor crater superimposed over Vienna. And you see, if a crater like this would form, it would immediately obliterate the whole inner city here, where we are, would all be gone, would be in the crater. And just for those who are not yet have walked around in Vienna here, I put St. Stephen's Cathedral in the bottom of Meteor Crater here, so you can see the size relationship. And if you walk up a couple of hundred meters in this direction there, you go to the actual St. Stephen's Cathedral, and it's damn big. So, excuse me. And if we would have such an impact in Vienna, this is right after the impact happens, and this is afterwards, well, most of the city of Vienna would be gone. Let us not forget that the object that made that crater is only a third of the size of that cathedral. So a relatively small object, about 50 meters in diameter, makes a crater that is 1.2 kilometers in diameter. And this is, of course, the topic that at the Planetary Defense Conference we're talking about. If such a small object comes in there, do we know it in advance? What can we do that it doesn't obliterate a big city or something like that? And we know these things happen all the time. We just had the 10th anniversary of the Chelyabinsk object exploding in the atmosphere, and that was just a 20-meter in diameter object. So, and that came out of the blue sky. Nobody knew in advance it was coming. So these things happen. The smaller, the more common. The bigger, the less common, fortunately. But still, you know, this is the topic of this conference. And do we know everything? Those are some of the objects that could get dangerous. We're in the middle of a cosmic shooting gallery. Can we do anything? Well, we'll hear from the speakers after me. Thank you very much for your attention. So now I'm putting on my moderator hat. Any questions that are urgent here or that we cannot talk about downstairs over a drink later? I don't see any urgent questions. Good. So we're catching up with time very nicely. So now I would like to invite Lindley Johnson, who is the first Planetary Defense Officer. So he will be, no, I'm not going to say that, which Hollywood actor we're going to compare him to. He's not going to ride the space shuttle either. But he's going to tell us what NASA is doing about defending our planet. Lindley, please. This is this kind of strange thing that maybe is a pointer and this is backwards. So. Okay.
Thank you very much.
Take care.
Good afternoon. Pleasure for me to come here and talk to you about our planetary defense program at NASA, whose objective is that something like Christian has just shown you won't ever happen to us again, at least not in a populated area. The Planetary Defense Coordination Office at NASA has been in existence now for about 7 years, although NASA has worked to discover these objects and learn about the asteroids and comets that come near the Earth for about 25 years now. But as our efforts increased, we felt it was important that we have a focused effort by the agency to undertake this task. So the Planetary Defense Coordination Office was formed to oversee the projects that NASA directly sponsors in this area, but also since NASA, if we got into a threat situation, isn't going to do it on its own, we need the capabilities and assets not only across the U.S. In our agencies, but internationally as well. So under our charter as well is to work with, plan and coordinate activities within the U.S. government, interagency, and with our international partners around the world. And what you're seeing here, a Planetary Defense Conference, is part of those efforts. So we're tasked at NASA with finding any potential significant impact threat to the Earth, be able to tell leadership, decision makers, how disastrous it could be based on what we can find out about the object, its size, those kinds of things. And then also develop strategies, technologies, and techniques whereby we might be able to prevent such a disaster if at all possible. Our guidance comes from a White House document that, if you're here at the conference, you're going to hear more about. But in 2018, this interagency guidance was released by the White House, guided by the Office of Science and Technology Policy in the U.S. With these 5 goals, kind of similar to the tasking to the Planetary Defense Coordination Office. Sometimes we do work in sync across the U.S. government. But I also want to point out in here that international cooperation and collaboration is a very important part of our goals in working in this area. This is a chart that shows how we organize our efforts at NASA in this mission area. And you read it kind of like a clock. Up at the upper right, and the most important thing that we do, the thing we've got to do, is find these objects. If we don't know they're out there, we can't do anything about them. And the earlier we find them, the more the options we may have. So finding them first is a large part of our efforts, and kind of why I use the subtitle for my talk is the only way we can protect the Earth is finding these objects one rock at a time. And then we are also doing a good deal of effort to characterize this population of objects. And both from an overall general characteristics of the population of near-Earth asteroids and comets that are in orbits that can bring them near the Earth over time, but also as specific objects of interest, being able to focus in on that object that may represent an impact threat sometime in the future. And the capabilities to be able to do that both with facilities here on Earth and in space. Then a good deal of our effort that doesn't cost as much as space missions, but is also equally important to what we do, is planning and coordination. And as I said, across not only the U.S. government and the agencies that might be involved, but internationally as well. And I'll talk about a couple of those areas in the future. Then this sector that all the Hollywood movies are about is mitigation. What are we going to do about an asteroid or comet that we find on an impact trajectory of the Earth? And testing technologies and techniques like DART, which you're going to hear about more, is in that area. And then, of course, we need to be able to see how successful we are in all these areas. So assessment of our capabilities and our progress is also an important component of our program. This just shows the facilities, observatories around the world and in space that NASA directly funds for searching for these objects, gathering observations to determine their orbits. And we've recently expanded our capabilities into the southern hemisphere with a couple of relatively small half-meter telescopes that we call our Atlas system, and also working with the U.S. Space Force and the Royal Australian Air Force on a telescope in Western Australia called the Space Surveillance Telescope. It's a part of our overall effort in mining data from all the images of the sky that they are taking. Our one space-based capability, NEOEYES, that's actually a repurposed space telescope that was originally designed for an astrophysics mission, but we quickly figured out it was going to make a great asteroid hunter too. It only had a one-year astrophysics mission, and after that was over, we took it over to be a dedicated asteroid hunter and characterization capability, since it operates in the infrared wavelength and allows us to make higher precision determination of the sizes of these objects. So those are the capabilities that are directly in our NASA program, but we also work with a lot of other observatories around the world, sponsored by other space agencies and institutions. All this effort is coordinated internationally through negotiations that we've had under the United Nations Committee on Peaceful Uses of Outer Space, in particular the Scientific and Technical Subcommittee that meets here in Vienna every year. So I get to come to Vienna about once a year to attend that meeting and report out our activities. And under those negotiations, two entities were established. Now, these are not UN organizations, but they are international entities where members of the United Nations have agreed to collaborate in this area in dealing with the near-Earth object hazard. And the first one is the International Asteroid Warning Network, and this is observatories, orbit modelers, researchers around the world that have agreed to join together to find potential threat out there and collaborate with our observations and information so that we have the best information available about any potential impact hazard. And that effort, operational network, if you will, is coordinated through NASA and our work at NASA, but it's participation from around the world. And the other form is the Space Missions Planning and Advisory Group. This is a forum for national space agencies and offices to work together on technologies and techniques that could be used to deflect an asteroid in space should we find one. And so we've encouraged nations around the world to join this effort so that we can get everybody on the same page. The IWAN now has over 50 signatories to it from some 20 countries around the world, observatories that participate with us in this endeavor. And then the same page members, 18 member space agencies, offices, and institutions. And I think most of you in this room will see your National Space Agency up there, but if you don't, tell your space agency they should become part of the same page. So let's get into what we're finding out there, one rock at a time. Just this year, most people don't realize that asteroids, thankfully small asteroids usually, come between the Earth and the Moon all the time. And so far here in just the first 3 months of this year, we've had 17 known asteroids come within the distance of the Moon. One is as large as the Tunguska impact, which Christian didn't talk about, but that was estimated to be about a 40-meter object that impacted in Tunguska, Siberia in 1908 and destroyed about 800 square kilometers, 800 square miles, 2,000 square kilometers of luckily just forest. Probably killed a few reindeer too, but as far as we know, only a minor human loss in that impact. And then 3 of these objects are could be as large as the Chelyabinsk object that Christian did talk about in 2013. So these things are coming by all the time, and it's just a matter of chance that they pass by instead of impacting the Earth. But space is a big place, and a major impact is a very rare event. But 2 of these have come also within the distance of the geosynchronous satellites. And we also have an effort where we inform the operators of spacecraft in Earth orbit that these close approaches are happening and could represent a collision hazard. Again, an astronomically rare occurrence, but it could happen. Luckily, those are all have been very small and would have been disintegrated by Earth's atmosphere should they impact. But there was one known impactor, and maybe you heard about it. A small object was discovered on February 12th by an Hungarian observatory, one of the, well, I wouldn't refer to him as an amateur, more of a pro-am astronomer that provides observations to us and to the Minor Planet Center. So this object was discovered and observations sent in arrived at Minor Planet Center about 6 hours before we were able to determine from those observations that it would impact the Earth. The alerts went out for observatories around the world, in this case mostly Europe, because they were in the ideal position to observe this object, to provide more observations so we could narrow down this area of impact where the object could impact. And initially it was this wide swath here, and as we got more observations in, orbit modelers were able to narrow that impact area down to where it's at. There it is, right there, just off the coast of France, there in the English Channel, and we were able to notify folks, and even in public media, Twitter feeds and such, that this impact was going to occur. And so people were able to go out and watch this harmless impact of an asteroid, and was seen from both sides of the English Channel. So in this case, nothing to worry about, so it really wasn't a warning, but an opportunity to actually see this phenomena. But it's also a great test of our capabilities to detect, track, and predict impacts, because enough observations came in a short period of time, just a few hours, to accurately predict when and where that impact was going to occur. We've also, just in the last couple of weeks, had a couple of high-profile objects detected, both reaching what we call, on our Torino scale, the first rating, 1 in 10, so not of really any public concern, but an alert to astronomers that we want to get more observations on these objects. Both of these were fairly significant in size. We wouldn't want them impacting anywhere near a metropolitan area, certainly. And the impact probabilities, which put them on the Torino scale rating, got to be less than 1 in 1,000, and that's when we start to pay attention, although don't issue formal alerts yet. on both these objects, but as more observations come in and the uncertainty zone narrows, as you saw in the case of EB5, then it drops off of this rating scale because the Earth is eliminated from being in the area of space that the object will pass through. 2023 DZ2 was a close approach, came between the Earth and the Moon a little over a week ago, and therefore became a prime target for characterization campaign. And so observatories around the world, both optical, infrared, and radar as well, were able to take observations of this object so we can learn more about their nature. So where are we at in finding everything that's out there? This is the current cumulative chart of everything that we found, some 31,500 asteroids of all sizes that are in orbits that can come near Earth since NASA's search program originally began in 1998. The ones that we are looking for, because we're tasked from Congress to find everything that's 140 meters and larger in size, 140-meter object, were it to impact, could devastate a statewide area in the U.S. or a European country. So we don't want those certainly to happen. That would be an existential threat, to a region or state. This is the overall discovery rate over the last couple of decades. We're finding now, with all the observatories around the world that are operating, a little over 3,000 a year of all sizes. And so far this year, we're a little behind because of some of the weather and such conditions that ground-based observatories have to deal with. But the observing weather is particularly good in the fall, so we're hoping we'll be able to catch up as the conditions are more favorable to finding these objects. Of the 140-meter and larger in size, as I said, that we at NASA are directly tasked with, we're finding a little under 500 a year of that size and larger. But that's not a rate that we're particularly satisfied with because the estimated population of these objects, 140 meters and larger, is thought to be about 25,000. And we've only found a little over 10,000 to date, so we're only about 42% complete after 25 years or so of searching. So to accomplish this tasking from Congress, we've got to up our game, so to speak, because at the current rate, it'll take us another 30 to 40 years to complete the catalog of this population and know everything out there that could represent a threat to the Earth. So we want to at least cut that time in half. Our plan to do that, currently ground-based observatories are looking at what we call the area of opposition opposite the sun, better known as the night sky. They're limited to looking in the night sky. We have this one asset in space called NEOEYES, but it has a very narrow field of view. It can only look a degree or so perpendicular to the Earth-Sun line in space, and then tracks around with the Earth to cover the whole sky in 6 months. We want to be able to find things faster than that. So we've undertaken a project called NEOSURVEYOR. This is a space-based infrared telescope specifically designed for this purpose, to find these near-Earth asteroids in a much shorter period of time. It will find 65% of that population within 5 years, and the entire 140-meter and larger after 10 years of operation. And also, with that infrared data, be able to directly estimate the size of the object too, as opposed to us having to spend additional effort, weeks and maybe even months, before we really understand what size range that we're dealing with. And NEO-surveyor's field of regard, it will be positioned at Sun-Earth L1 point, the gravity stable point, so it can follow along with the Earth around the Sun. And once a month, it will survey this entire region that is highlighted there. So do a much faster survey of the sky this way. So we find with this project, which will launch not later than 2028, within 10 years, this population. And NASA approved this project for development and launch just late last year, so 2022 was a big year for planetary defense for us in the U.S. with both the DART mission and now approval of the NEO-surveyor mission. And as I said, NEO-surveyor will sweep out the sky from the Earth, Sun L1 point. So this shows it, well, maybe it won't show. It operated. My animation here is apparently not working. Let's see here. Yep. Well, it's very exciting animation. Yep. There it goes. Okay. So it monthly sweeps out the sky, discovering all these objects and this, detecting this swarm of asteroids of all sizes down to its limited magnitude anyway. And over the course of 5 years is what this shows. And these are actual animations of the objects and the observations taken to map out their orbits. So you're seeing a realistic depiction of the population of near-Earth asteroids. But don't let it scare you, because this project is designed to find them all well before they ever represent an impact threat to the Earth. That's the whole idea behind it. Because the earlier we find them, the more options we will have to do something about them. Oops, can I get to the next one? I restarted it with that click. I might need some help to get it to go to the next slide. Okay, thank you. And so, you know, talking about what we might do about them, well, the DART mission test of technology you're going to hear about from the other speakers here, so I won't dwell on that. But I also want to say, you know, DART is a part of a larger international collaboration started back more than 10 years ago of the Asteroid Impact Deflection and Assessment, has evolved into the DART mission and the European Hera mission as a follow-on to DART going to the Dimorphos system. So that's all part of a larger effort in the coordination between NASA and on our international projects. And so with that, I'd be happy to take any questions that you might have.
Thank you, Lindley, for this great overview. Do we have questions? There is. Okay, here. Please wait for. Please wait for the microphone.
I have a question about...
This is Mark Boslow, by the way.
I have a question about 2023 CX1, the one that happened during the Super Bowl, yes, for at least us in the States. So I found out about that just by chance, from a tweet. But one of the things
That's the way a lot of people found out about it.
Yeah, one of the things I've been very interested in ever since the first one of those events, which was in 2008 TC3, is getting information very quickly to the public, potential observers with, you know, who in this case would have been able to rush out to the seashore in France and England with their cameras, and if there was a way to do that, we could get a lot more data. Could I1 have a role in getting that kind of information out quickly to everyone?
Yeah, well, I think you saw some of the preliminary examples of that in this case, and that we did get tweets out ahead of time and got information out. But I agree with you. It could be a better effort, more widely publicized, and those are some of the notification procedures and sets that the IWAN is working on how to best do that. You know, it's kind of a delicate balance between getting information out fast, but getting the best information available, accurate information versus what you may see in other places on the internet. So it is something we're working on.
Do we have other questions? Yes, in the back there.
It's not allowed to ask a question either.
Thank you, Dr. Johnson. Wonderful talk as always. In going to these international meetings, so there have been reports that the Chinese Space Agency is considering a planetary defense mission, but there aren't a lot of details that have been made public. Is there anything that they've reported to Same Page or any of these other international organizations about that mission that you can talk about?
Yeah, well, the Chinese are members of both IWAN and Same Page. The Purple Mountain Observatory, among others, in China provides a lot of observations to the minor planets there. But you're going to hear a couple of presentations from the Chinese program here at the PDC. So, I think they are starting to be involved, tell us more about what they're doing, and that's the whole purpose of this conference and Same Page IWAN is to share what everybody is doing, collaborate with it, and be transparent about what's going on.
Other questions? I have a quick one myself. You showed the NEOWISE. How long is that still going to be operational estimate? And is the new Surveyor one going to replace it totally, or what's the plan here?
Yeah, well, NEOWISE, the ever-ready bunny of space. NEOWISE was designed originally for just a one-year mission, and here we are 12 years later. Still going, but its orbit, since there's no way it doesn't have fuel on board to make up orbit or maintain its attitude, here in the next year, the Earth's atmosphere is really going to start interacting with it a lot more. We have just agreed to another extension of the NEOWISE mission through July of 2024, which is our current estimate as to when it's going to reach a natural end of life because of the atmosphere. So just another year for NEOWISE. And then, of course, NEO-Surveyor is the replacement, but 4 years later.
Thanks very much, Lindley. Thank you very much again. Now we come to the topic of the DART mission, and a presentation about the DART mission in general and how it worked and so on will be given by Elna Adams. She's at the Applied Physics Laboratory of at the Johns Hopkins University, and she is, I think you're the manager of the whole scientific effort at least, so will be very interesting.
Thanks, Christian. All right, first, I'm the DART mission system engineer. Our managers are over there. I will not take that. However, we are responsible for making it work, so that's a plus. So today I will talk about DART, the Double Asteroid Redirection Test. What does it take to actually hit an asteroid? And we'll start in the beginning, which is all of these mitigation techniques that Lindley mentioned, Christian mentioned, all of them rely on the fact that we want to go to the asteroid and we want to change the orbit of the asteroid in such a way that it misses the Earth. Some of the mitigation techniques, you know, in the worst case scenario, you need to actually destroy the asteroid. But the goal usually is to slightly tap it and move it out of the way. And that's what DART is all about, a slight tap to an asteroid to see if we can actually do it in real life, because we do a lot of observations, we do a lot of experiments in the lab where we hit things with really fast projectiles and see the explosions. But this was the first test actually in real life on an actual celestial object where we rearranged our solar system for the first time. So with that, this is DART. We are part of the Planetary Defense. You have to show this graphic. Anytime you give a planetary defense talk, you have to show this graphic. Otherwise, Lindley comes after you. We are part of the mitigate strategy. And this is basically DART. Go and whack an asteroid and see if you can move it. Of course, real life is much more complicated than that, so I'll tell you a little about that. You can see we're hitting an asteroid. We create a big plume. Nancy will talk about that right after me. What happens after we created this big plume, and did we really move the asteroid? So I'll take you up to the point of impact, seeing the impact, and then I'll hand over and we'll finish up there. So First things first, give everybody an orientation on our two favorite asteroids. We went to the Didymos system. The Didymos system is consistent of two asteroids, one larger one, Didymos, 780 meters, so somewhere between the Burj Khalifa and the One World Trade Center. And then the other one is Dimorphos, and that's the one that we impacted. Didymos, main asteroid, Dimorphos orbits around Didymos. And Dimorphos is 163 meters. What we actually find out is it is not exactly 163 meters. But before you get there, you have a lot of reference missions. People have been observing these asteroids for quite some time. And we'll talk about that in a minute. But you can also see DART spacecraft on that scale as well. And it's about 19 meters in size, so about between a bus and Arc de Triomphe. So this is the Didymos system itself. You can see large asteroid Didymos in the middle. And here's Dimorphos. Oh, by the way, we are very happy that these names are here now. We used to call Didymos A and Didymos B because we didn't really have a name until a little while ago. Dimorphos actually means it's of Greek. So Didymos is of Greek twin, and Dimorphos is of two shapes. One shape before, and after DART smacked it, a different shape. So you can see that DART came over, it hit the asteroid Dimorphos, and was able to kick it into a different orbit. So our goal of DART was go to the Didymos system, find Didymos and Dimorphos, hit Dimorphos, change its orbital period around the larger asteroid, and then observe what happened. So how do you observe what happened? You do that from the ground. So originally when we started, this was a mission that was both a European Space Agency mission and a NASA mission. They were going to get there at the same time, and this mission aim was going to observe the asteroid. Well, things happen. Harry's getting there a little bit later. So we had to figure out a really good way of doing it from the ground. And that's what the telescopes from the ground did after the Didymos impact. They actually observed the asteroid, and they're able to tell the change in the period by looking at the light coming from the asteroid, from Didymos, the main asteroid, and seeing it dip every time Dimorphos crosses in front of it. So that's how we determined the new orbit for Dimorphos. And that's how we actually measured the orbit before, and that's how we knew that it was a binary system, because we didn't really know much about Dimorphos at all. So I'll tell you a little bit about the DART spacecraft, and NASA is a technology demonstration mission for NASA. Number one thing is we demonstrate the technology to be able to redirect an asteroid. Seems very straightforward, but it involves a lot of different pieces. It involves the smart navigation system together with our telescope Draco that combined together allowed us to actually impact the asteroid. We also had a lot of other technology that we demonstrated for NASA too. A new type of ion engine called NEXT-C, new types of solar arrays we actually had solar arrays, and then they had baby solar arrays on top of them that we demonstrated as well, called transformational solar arrays, which are special concentrators. We also demonstrated a new type of antenna called radio line slot array, and sometimes when you demonstrate new technology for NASA, you get to use it on the next mission. So we're using this new type of antenna on our next mission called Dragonfly that's going to go to Titan and fly in Titan's atmosphere. It's a rotorcraft. And we also demonstrated the rollout solar arrays. And may I just say, as a systems engineer, the most frightening time for me was not the impact, actually. It was those 40 minutes as our solar arrays rolled out for the first time. It was all autonomous, rolling out. A lot of mechanisms had to fire precisely, where the solar arrays that look like blankets rolled out and snapped to be really taut. And that's what actually powered us all the way out to Didymos. So on top of that, we carried a little CubeSat with us. So it's a small spacecraft, size of a bread basket, maybe. I don't know, is it a bread basket or is it something else? It's been a long day. So it's a little bread 6U CubeSat from the Italian Space Agency. We brought it with us. This is the first planetary CubeSat that was deployed at the asteroid itself. And with usually CubeSats you deploy as your rocket goes up, you release all your CubeSats, everybody's happy. But in our case, we actually brought it all the way to Didymos, and we deployed it 15 days prior to arrival to Didymos. And then after we impacted, Lychee Cube flew by what was left of DART, which was vapor, and a lot of ejecta coming out of Dimorphos, and was able to take amazing pictures that you'll see and from Nancy. So you can't help it, but we started integrating our spacecraft. So DART has been around since about 2015. We had our preliminary design review in 2018, and then moved on and started integrating DART together in March 2020. If you remember, something else happened in March 2020. So it was really exciting. We had one of our reviews, and one of the team members came in coughing a little bit, and then we were all in quarantine for 2 weeks. Right after that, we got back together again and started actually integrating our spacecraft. So since May of 2020, we've been integrating the spacecraft, putting it all together. You can see closing out our panels with all of the electronics boxes, testing it as we went through all of our different testing, installed our high-gain antenna. This is the shower head that brought back all those amazing images back to Earth. Installed our crown, the NextC engine, did a lot of electromagnetic testing, thermal vacuum testing. These are the rollout solar arrays. You can see the really long blankets that are rolled up on the spool, and here they are actually in the rolled up position. We also installed Draco, which is our imager, our telescope, the eyes of DART. The whole spacecraft came together. We tested it. We brought in Lychee Cube. These are our Italian colleagues. You can see that even with masks on, they look extremely happy. So in September of 2021, we went to SpaceX at the Cape, brought this over on a truck. Here's our spacecraft, and the spacecraft itself, it's human size. It's 2 by 2 by 2 meters, so I'm 2 meters tall. You can imagine it's not a very big spacecraft. It's just the solar arrays are really giant. And those of you who had a chance to do the VR downstairs, you can really see it, and I think we'll have it available afterwards. You can put on the virtual reality glasses and actually see how big the spacecraft is. It's a pretty fun experience. Point is, we launched in November of 2021. And here's
9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
So I'm told that the night was beautiful and the launch was gorgeous. A lot of us were in the Mission Operations Center with no windows and did not get to see it, but we did get to see this.
The job of Falcon 9 was to get DART on its way to the Didymos system. At this point, we've gotten enough velocity, enough speed to send DART off towards the Didymos system. And right now, we're in range of the ground station, so we can get all the data from, and so we can make sure we can actually capture the separation confirmed. And we just heard the call out for spacecraft separation. You can see the video of the DART spacecraft on its way, heading on its way to the Didymos system.
What a spectacular view.
Well, yeah, we thought it was a spectacular view because this is the first time we actually got to see our spacecraft get off a rocket and go. So we knew that it made it that far, right? So first step, winning. So we launched in November of 2021. You can see this is the orbit of the Didymos system. You know, it gets as close as far as 2 AU from the sun. It gets really close to Earth. And DART it stayed with Earth pretty much the whole time. And it impacted right as, how does this thing work? Oh, here we go, here we go. You can see all of them are very close to Earth, all at the same time. And that was specific in order to be able to have observations from the telescope. We can also send images back to Earth, real time, basically, and have really great things. As I said, we knew fairly little about the object we were going to hit. There was a lot of observations of the Didymos system. People have been tracking it since 1996. In 2003, there was a really close approach where people were able to use radar to create a great shape model of Didymos. We thought we knew what it looked like. It surprised us quite a bit. But we really had no idea what Dimorphos actually looked like. And because we just had an approximate size, and the telescopes gave us an idea of where it was going to be at the time of arrival. And that was really key, right? If we got there at the wrong time, Dimorphos would be behind Didymos or in front of Didymos, and we were watching it with the visual camera, so we would miss it completely. So that is Draco, our instrument. It was doing a lot of observations. During flight, we were training it to make sure that it can actually do what we said we were going to do. For example, this is, sorry, oh, go back. Ah! All right, we also trained ourselves and rehearsed all of how we were going to celebrate. I'll just leave it at that. All I'm saying is that we spend a lot of time training Draco and smart navigation on other things like the moons of Jupiter. We actually watched the moons of Jupiter come out from behind Jupiter, and we were able to track it and pretend like it's Dimorphos and Didymos for the first time, and have our camera actually track it and make sure that we would be able to find Dimorphos and impact it. Because it's really hard to do because these asteroids are really dark. The only thing that happens is they reflect sunlight. So what you're seeing with asteroids itself is only the part that is actually reflecting the sunlight. And that's the part that you go to. So if you're trying to hit the center of the asteroid to transfer all of the momentum in there, you actually sometimes have to correct yourself. So about 45 days prior to arrival, we detected Didymos for the first time through our camera. As we got closer in, we released our CubeSat. About 10 days prior to arrival, we got DSN to have continuous coverage. So we were actually talking to the spacecraft the whole time. At 8 hours, we were all in the Mission Operations Center. All of us were ready. We were going to do this today. We were ready. We had 21 contingencies that we could execute in case something was going wrong, especially the one that contingency number 21, which is what happens if you miss. And we didn't really want to miss. So this whole thing was live to the whole world, and at 4 hours the spacecraft became completely autonomous. So what does that mean? Means that we on the ground were just watching it go. And we were not sending it any commands. It was bringing lots of data down, so we were making sure that it was doing everything correct. But the spacecraft was doing everything itself. It was finding Didymos, and it was going towards Didymos. And then at 73 minutes prior to impact was the first time that it detected Dimorphos for the first time. And at 68 minutes, it formed a stable track, which means that it was ready. The moment we let it go, it would start guiding itself towards Dimorphos, which is the smaller moon. At 50 minutes, it switched over, started guiding itself in. It closed in and precisely locked on it at 20 minutes. And at 2.5 minutes, it stopped all maneuvering. And at that point, it just started gliding itself in. So this right here is 10 times the speed of the last 5 minutes of the life of DART. And this is from 7 million miles away. We're streaming images all the way in. And you can see Didymos doesn't look exactly like the shape model did, does it? But, and then we're seeing Dimorphos for the first time. This is about a minute prior to impact. You can see it's finally coming closer and closer. And then in the last few seconds, you get these amazing images of DART impacting, and you still get one last image right before the impact. And then, of course, we're all happy, and then Nancy's going to take over. I'm ready for that drink. No, I'm just kidding.
So do we have questions for Elena? Yes, please.
One thing which would interest me was you had these last few pictures. Could you calculate the distance to the actual object on that point? Or how far were you away?
Yeah, we did, and Nancy has a couple of slides on that, so
Okay,
I'll let
perfect.
her talk about it. Yeah, good lead in.
Thanks a lot.
So just to give you a feel, we were moving at 6.1 kilometers per second. So that gives you a feel for how much reaction time we had in order to be able to do anything.
Other questions? Yes, please. Back there.
Hi, I'm Wendy Caldwell from Los Alamos, and my question is, I wonder if you could speak a little bit more about the extra challenges this mission specifically had because of the pandemic, and how you mitigated that, and how that affected the overall mission timeline and things like that.
Sure. So as I said, we started in March. We started integrating in March. And the first thing we had to do was to retrieve our spacecraft structure that went to Airjet, which was in Redmond, California. And if you remember, that was one of the hot spots for all of the activity at that time. And so in May, one of the people who's sitting over there on the left, Jeremy, wave your hand, actually had to be out there with the rest of the team. They worked in shifts. Only a couple of people could work at a particular time. They were trying to distance as much as they can, but frankly, the spacecraft is 2 meters, right? There's only so much you can do 6 feet. And so we all wore a lot of masks. We came in every day. We also came up with some novel ways of testing our spacecraft where it was done. A lot of it was done remotely. Usually in the integration room, you would have 30 or 40 people there at particular test time. We did a lot of that online. We set up electronic systems to be able to tell the spacecraft, test the spacecraft so that only 6 or 7 people had to be there at a time. And they were socially distanced. We did a lot of shifting. We did a lot of crying. No, I'm just kidding. Well, there was some of that too. One of the reasons why we slipped launch was not because of pandemic so much. We originally were supposed to go in August. We went in November. And one of the reasons why we didn't go earlier was because we had a failure on our instrument. Not on the instrument itself, on the engineering model. So we spent a little time investigating. We had a lot of replanning. But overall, I think the team really gelled together during the pandemic because honestly, we had no choice and we had to get the mission done. So it all worked out for the best. Thank you for that softball question, so I can point out other team members in the audience.
Any other questions? Yes, please.
Hi, first of all, I enjoyed your talk a lot. You're an amazing speaker.
Thank you.
And I'm interested in, are there any precautions taken to avoid, or do we think about microbial contamination? Is that something?
So luckily, most of the ejecta that we created would fall back to Didymos. We had contamination control because we did have an optically sensitive instrument. Mm-hmm. So we did have to do a lot of contamination control on the spacecraft. Because this is an asteroid, we did not worry so much about planetary protection itself. We were category 4 in planetary protection category. This was not a Mars mission or Europa mission. We weren't drilling through the ice looking for microbes. So in that sense, the only contamination control that we did was to make sure that our camera is not covered in dust, because then we would mistake the dust for the asteroids, which would make us feel very stupid.
Thanks.
I have a quick question myself, but maybe Nancy is going to get to that too. But what was the mass difference between the impactor and that small asteroid?
So the mass of the impactor was about 600 kilograms, and the asteroid itself was in 5 million. Oh, sorry, 5 billion kilograms, order of magnitude. Yes, it was how much ejecta we blew off was in the millions of kilograms. But I'll let her talk about it.
Yeah, okay. Okay, I guess we'll let you get away here. Thank you very much. So our next speaker is Nancy Chabot, also from the Applied Physics Laboratory at the Johns Hopkins University. Nancy has had a long career in working on meteorites. Those are the small things that fall down on the Earth, and now she's kind of looking at the source where they come from. She did some work at the University of Arizona, I believe, and was also at NASA Johnson Space Center in Houston for a while. And there's something we actually share in terms of history. We've both been to Antarctica looking for meteorites there. Me, however, a long time ago. Antarctica was really frozen over, and she was there more recently. Anyway, and currently, and this is another hat Nancy is wearing, she's currently the president of the Meteoritical Society, that society that studies and the people that study all these things that fall from the sky. So, Nancy.
Well, thank you. It's a real pleasure to be here today. And I don't know, in case anybody forgot where we left off, which is pretty impossible, we're still going to start on September 26, 2022, the day that humanity first moved an asteroid. Along with that great accomplishment, this was broadcast worldwide by NASA.
Unbelievable
Over 1 million people concurrently tuned in to this broadcast and watched this live.
Oh my gosh.
There you see Lena in the Mission Operations Center along with the rest of the team.
Visual confirmation.
Those final images streaming back. Draco working until the very last seconds. Even in the final partial image just about to come. And then we have Impact, an amazing moment, a huge accomplishment, and a lot of celebration, and a lot of time went into this. I mean, like Lena talked about, building a spacecraft during COVID brought people together, gave you a meeting. It was great to get to this future moment where you could celebrate this. So this was a huge accomplishment, a huge challenge, hitting a small asteroid in space that you've never seen before when it's 7 million miles away, and doing that autonomously while moving at 6.1 kilometers per second. And so rightfully, there was a lot of celebration going on as well. And while we were celebrating, LICIACube was working. So the Light Italian CubeSat of imaging of asteroids, that little CubeSat, sort of briefcase size, made its close flyby about 3 minutes after DART's impact into Dimorphos. And it wasn't able to send those images back in real time. It stored them on board, and then it sent them back in the days and weeks that followed. So what you're seeing here is those images then put together into a movie. And so you're approaching, and you can see the ejecta coming off of Dimorphos, the result of DART's impact, and then LICIACube actually turns around once it makes its closest approach here and looks for as long as it can while it flies on by. An amazing accomplishment for a briefcase-sized spacecraft operating 7 million miles away from Earth autonomously. Italy, this was a great contribution, and it's been really, really proud of this accomplishment, as they should be. I like to show this image too, which is just one of those ones from that sequence of movie that I just showed. And because, there's a lot of different brightness levels in each of these images. So when you just have to show one movie, you don't kind of do justice to just what an amazing data set this is. So what you're seeing here is just one of those images captured by LICIACube, where each of the boxes is like a different contrast stressed, a factor of 2, a 2, 2, 2. So you can see all that amazing fine detail that you're getting there in the ejecta, in these rays that are going off in different directions with different morphologies. This is a really rich data set that we're continuing to study. So it wasn't just LICIACube that got busy, though. Telescopes around the world also started to turn their gaze back towards the Didymos system. We actually even just updated this map the other day, and it's an amazing international effort, the observing campaign that has been DART's impact event here. I mean, you can see all 7 continents involved: North America, South America, Africa, Europe, Asia, Australia, New Zealand, even down in Antarctica. Telescopes in space, Hubble Space Telescope, JWST, and Lucy also have contributed. And this wasn't just by coincidence, like Lena showed, and I'll just sort of show this again to make the point. The timing of DART's impact into Dimorphos was chosen such that the distance between Earth and the Didymos system was minimized. So Didymos goes around the sun, the Earth goes around the sun. Sometimes they're on the opposite side of the sun. Not an awesome time to use telescopes. But you can see that this timing here in the fall of 2022 really was the ideal time to do this first test of asteroid deflection, where the DART spacecraft is going to go there. It's going to intercept Didymos. These look close together, still 7 million miles away. But you can see from the astronomical perspective, this is like next door. The telescopes have gotten better data on the Didymos system than they ever have previously. And you can also see that that continues for many months after DART's impact from looking at this diagram. At the moment of impact, the telescopes in Africa were in the ones that are best positioned to look up at the night sky and capture the moment of DART's impact. And what you're seeing here is from a telescope in South Africa, immediately before and right after, with this fast plume of material being released. This was also shared across social media while we were celebrating, while LICIACube's working. People are posting these to Twitter, and so the effect of DART was immediately seen by these telescopic facilities, not just this one, but across other ones in Africa and as well. 5 hours after impact, Hubble and JWST looked at the same object in the sky for the first time. And this is a challenging object. It's close by, it's moving fast, but they captured these spectacular views of the ejecta coming out hours afterwards. And again, sort of mirroring what you saw from LICIACube just a few minutes after impact with these complex ejecta rays and structure. 2 days. This is Chile, a telescope in Chile. The tail has started to form. You're getting this tail of dust and debris going off down in one direction. You sort of see the original cone of the ejecta that you had sort of at the 12 o'clock and at the, sort of 8 o'clock position. And then there's this tail of ejecta going off in these other directions, just 2 days post. 12 days post, this is a spectacular image from Hubble Space Telescope. And I'm just showing you some highlights here. I could show you so many more images than this, but you can see how the tail has evolved into 2 tails temporarily. And then you have these wings of the ejecta sort of spiraling out from this double system. This is a great movie, actually, that captures the first month. This was just published 2 weeks ago, actually, from the VLT in Chile. And so what you'll see, and it'll repeat here, is there's immediate brightening after DART's impact, and then the evolution of the ejecta and that formation of that long tail as you have this month going on afterwards. So again, this initial brightening and then the formation of the long tail capturing this first month. But jumping forward, because everybody wants to go downstairs eventually and have some refreshments, so 52 days post-impact, there's still a giant tail. Here we are, 52 days, and this is from Lowell Discovery Telescope in Arizona. At this point, people are estimating that the tail is about over 30,000 kilometers long, and the best estimates of the amount of ejecta in here are 10 million kilograms-ish. So that's sort of what you're looking at. The team works hard, so this is a holiday for lots of people, but here in New Mexico at the telescope, they were capturing this spectacular images, getting all of this data, maximizing what we learned from this unique opportunity that was DART's impact event. And Hubble Space Telescope has had this continuing observation campaign where every few weeks they're able to look at this system. So here you see November 30th, going through to December 14th, December 28th, again, a very long tail. It's getting fainter, though, you might notice here. January 19th. Here's March 1st, so just a month ago, and now you've still got this long tail. It's longer than it used to be, but it's also getting fainter. And I was kind of sad that the tail was going away, but people on the team have assured me that this is really great because we're seeing it all the way from the beginning all the way until the end. And so these observations for Hubble can continue for a few months to really see the full evolution that's going on. Telescopes on Earth are also continuing to contribute. This is one from the Lowell Discovery Telescope in Arizona just a few weeks ago on March 14th. Estimates here are 70,000 kilometers long for the tail. Where exactly is the end of the tail is a bit of an esoteric question, but you get the idea. It's long, it's getting fainter, we're tracking the whole thing. It's been spectacular. But of course, the real reason to do this wasn't just the spectacular ejecta to see there. You want to see how much you move this asteroid, and hence the double asteroid system, like Lena so nicely talked about. And so we knew from the telescopes ahead of time that Dimorphos goes around Didymos every 11 hours and 55 minutes. This has been determined extremely precisely through decades of observations. So 11 hours and 55 minutes, 11 hours and 55 minutes. So what DART did is it came speeding in at 6.1 kilometers per second. LiCiuCube was kicked off 15 days in advance. DART slammed into Dimorphos. LiCiuCube sped on by, capturing those images that I showed you and then sending them back to. And what that impact did of DART into Dimorphos is that it shifted Dimorphos into a slightly different orbit. So how much different was that? The DART spacecraft was surely not going to tell you. LiCiuCube just flew on by. The telescopes on Earth got back to work. And those observations showed that it was now 11 hours and 22 minutes. So the orbital period had been changed by 33 minutes. Because this was so big, we were actually able to announce this. NASA was able to announce this just 15 days post-impact. We were honored that this was done by the NASA administrator himself that said, today NASA has confirmed that DART successfully changed the targeted asteroid's trajectory. And like Lena said, this was done with one method being the light curves. And this shows the geometry of those initial observations there, where sometimes Dimorphos was in Didymos' shadow, and that would cause a dip in the brightness. And sometimes Dimorphos would pass ever so slightly and cause a shadow onto Didymos, and that would cause another brightness. So you basically do brightness versus time, you build up this graph, and you can see that this brightness versus time is tied very much to the orbital period. To show some actual data, this is just from those first few days following impact. Across the top, you just see brightness versus time, brightness versus time. There's actually 4 different telescope data sets combined here. They agree so extremely well, so you can't even tell them apart. There on September 29th and October 4th, you have a blow up of these brightness versus time graphs. And what you see is that the dip occurs where you have this 33-minute orbital period change, and you don't see a dip where if a DART hadn't hit Dimorphos, this 11 hours and 55 minutes, you would have expected it. But we're really happy as well to be able to confirm this with a totally different independent data set, and that's planetary radar. So using the Goldstone planetary radar and the Green Bank planetary radar, observations were made. And what's great about radar is that unlike the optical telescopes that only saw it as a single point of light, where you measure the brightness changing with time, radar can directly detect both Didymos and Dimorphos. So what you're seeing here are images from those radar telescopes that were captured in October. Right there in the middle is Didymos, and you can see that there. And if you've got good eyes or are used to looking at radar, maybe you've identified Dimorphos. If not, here's a little hint. There's Dimorphos. They're sort of in the green in each of them. So you're getting signal directly from both Didymos and Dimorphos. And what's important is the position of where you see Dimorphos in these images is actually different than where it was expected to be if you hadn't bumped into it, if you hadn't had this change, if it had only stayed at 11 hours and 55 minutes. So these two different data sets are giving exactly the same answer, this period change of 33 minutes. Observations have continued since months, since this was just published in Thomas et al. At the beginning of March, and it's 33 minutes has held up very nicely. All right, so what does this mean? So if DART had just bumped into Dimorphos and you had just transferred that momentum alone, you would have experienced a period change of about 7 minutes. So 33 minutes is much bigger than 7 minutes. And this was expected because we expected there to be some ejecta. But how much ejecta? How would an asteroid of a relevant size for planetary defense, 150 meters, actually react? This was one of the main reasons that you had to do an in-flight test for this technology, along with being able to hit a small object in space that you've never seen before. How would that object react? And what we found with DART, actually, is that the ejecta is actually even doing more work than just what you bring in with the spacecraft alone, that the amount of momentum that you're getting from there is really enhanced because of this recoil effect of the ejecta going off in the other direction. And our estimates, if you assume that Didymos and Dimorphos have the same mass, we know from telescopes that they have about the same composition. This momentum enhancement factor, where if you just had this 7-minute period change and you just bumped into it, would have been 1, is about 3.6. So it really means that the ejecta is substantially enhancing the amount of deflection, the amount that you're moving this asteroid. So the team now, with those sorts of basics of what's happened, is turning back to Dimorphos to try to understand not just what we did to Dimorphos, but to fully understand that process, because of course the goal here is to potentially apply it in the future when you need to. And so this is just a nice mosaic, actually, of Dimorphos that's made from the 10 highest resolution images at the end. And from these, we've actually determined the shape. Oh, sorry. You're right, back doesn't work very well. Can you go back a few slides for me? Back 2 more. Thank you. So what you can see here actually is that you can't really get very much of the shape of Dimorphos because you just sort of come in. But actually you got Diddy shine. So Didymos is off to the right of this image, and it's reflecting sunlight and lighting up the shadowed side of Dimorphos in those Draco images that were streamed back to Earth. And it's kind of hard to see here, but the little white arrows are pointing it out. But maybe you can see this is the full size of the asteroid because of this Diddy shine effect. So using that, we've been able to sort of estimate the mass of the better, but we're going to wait for Hera in order to get that full measurement. We've also named some rocks on Dimorphos because we need to talk about this thing. So, rocks on Dimorphos are named after percussion instruments because, DART banged right into Dimorphos, so it's very appropriate. This is all IAU approved as well, so it's appropriate there. But percussion instruments, Dole, because it's very distinctive, sticking off the edge of Dimorphos there. Punio is defining the coordinate system. But Atabake and Bowron and Kakavela are named because that's about where DART hit, and we need to be able to talk about that. Here's an overlay of this more specifics with the spacecraft over onto the top, hitting Atabake and hitting Bowron. And then right now, people are reconstructing this whole impact event into the actual topography, into what we've seen on that asteroid, taking the trajectory of the spacecraft, the model of the spacecraft, and running these simulations to fully understand what happened during DART's impact event. And to tell our colleagues just which parts that they created were destroyed first. So it turns out that one of the solar panels hitting Atabake was destroyed first, followed by Bowron, and then the main mass of the spacecraft hits after that, with a beautiful close-up of that star tracker sticking out there at the bottom. Maybe you're going to get it for the main mass first. But taking this then, we can put this into numerical models. So this is an idealized version of Dimorphos from those images, from that topography, from that shape model, that then can be stuck into numerical simulations to try to use that specific geometry to model what did Dimorphos expect, what happened when this happened. And so DART there again hitting Atabake and Bowron, those two rocks. And simulations like this is about where the team's at. This is just one example then of taking that information, running it to try to understand what you're getting. And so what you're seeing is this ejecta that's come out. This is all again in the simulation. And there's obviously a lot of similarities between what you're seeing in the Lichia cube with this very wide opening angle for the ejecta, this very complex morphology because of the topography, because of the surface. And the team is continuing to work on this even right now. Along with the team that built DART at APL and across the country, we really have valued our international investigation team that's been involved with this. We have slightly over 300 scientists representing 100 different institutions in 28 different countries. I know a lot of people are here today who are on this team or are built the DART spacecraft, so maybe you guys could all stand up for a moment, please. You know I know who you are, so you should just stand up. It's been a great effort. We're very happy that we're going to have Hera follow on, that we're going to hear all about in a second. I have to show this, like Lena said, so I'm compliant with the Planetary Defense Coordination Office. Just one part of a larger strategy. If you were going to do DART, you would need to do it years in advance. This is a small nudge that adds up to a big change in its position with time. You can't do anything about the asteroids if you don't know where they are. And I like to show this one too, because I think working on this, at the end of the day, it is just a human-sized spacecraft that was made by people working together for years in order to do something that's never been done before. And it's an amazing example of what we can do working together. And we're going to watch this NASA video.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss. 4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.
It's an honor to be on this team, part of this great group that's made this happen, and thanks for having me here today to share it. Thanks.
Questions for Nancy? You have to repeat.
My favorite asteroid, I don't know, it's hard to pick just one, Lena. You know, I'll just go with Dimorphos to be very on brand at the moment, so there we go.
Okay, do we have any questions? Yes, please.
So a rather basic one. Let's think about the situation. You have found another asteroid, and now anyone says, okay, we want to hit it. How long does it take?
It depends on the specific asteroid, obviously. But in the recent decadal survey that we did in the United States for the National Academies of Sciences, we have this really nice graph where we did a lot of different scenarios about different asteroid sizes and things like that. For something the size of Dimorphos, you're looking at something that's 5, 10, 15, 20 years. 5 years being very, very sporty. Really, decades is much more that you want to be having in order to do this. And it depends on the trajectory, how much you have to move it, the size of the object. For something like Dimorphos, Dimorphos, that's sort of what you're looking at. Which is, again, why it's important. This can be really flashy. It can show like great movies. If you don't know where the asteroids are, you can't do anything about it. It's got to be part of this longer strategy. What's great is that once you do find asteroids, people, NASA, others, accurately track those for on the order of 100 years regularly. When they say this isn't a threat for the foreseeable future, that number is 100+ years. And so it's entirely reasonable to have this decades of warning time if you do that legwork of getting this survey in place, identifying these asteroids, and then being able to do something about it. So, and again, DART is just the start, right? This was demonstrating this technology for the first time. That's never been done. There are next steps that have to be done before you'd want to be in that situation. So I'm very hopeful that we're sort of like on this pioneering path where this first thing's been done and we continue to make these steps. NEO-survey are very exciting, but then what comes after that is an exciting future as well.
Other questions? Yes, please, over there.
Nancy, congratulations, and Elena, the same to you. So you hit it right on, but was there an error ellipse? Can you calculate what the performed or what the software wanted to go to and where you actually hit? What was the ellipse?
Yeah, so this was just published in the Nature paper March 1st as well, but it was within 25 meters of the center of figure. And so it was aiming towards the center. That's what it did. The more the uncertainty there is, it was always an optical telescope, right? So you're working on the lit part of it, right? You didn't even necessarily know what the dark part was. We've estimated that shape now, but it was definitely like right in the center, and that within 25 meters is, conservative. It might even be closer than that. Oh, okay. And Lena says it was within 2 meters of where you were aiming at. Of course, you had never seen it before, so you were kind of just like aiming at Dimorphos, but Yeah, it did extremely well. I think we can't talk enough about that autonomous navigation software, right? That took it could have been so many different shapes. You could have had so much different lighting on it, right? And it was always supposed to go towards the center of that lit one, and its performance was spectacular. It's been really exciting to have that calculated.
Other questions? Yes, please, back here. First, maybe the lady further in the back.
Oh, me, okay. I'm the only one, okay. Hi, good evening, everyone. Hi, Nancy. So this is Nancy Wilson from Washington, D.C. Nancy, just so you know.
Nice.
So, based on the many years that we have discussed, the different deflection techniques, why don't you tell us just a little bit, if it's possible, about the background of how we, the community, decided to, out of all the deflection techniques that we discussed for many years, we ended up choosing DART, because I was part of those conversations, and I know how difficult it was for us at the end of the day, trust that NASA, in collaboration with ESA, future era going up, came about. Would you tell us a little bit of the background, please? Thank you.
Yeah, and I won't speak towards the collaborations or whatever. Lindley can jump on up here if he wants to sort of give some of that, because I think it's an interesting story for sure. The kinetic impactor technique, basically like crashing a spacecraft into an asteroid, was chosen for the first demonstration of a way that you would do mitigation because it was the most mature. It's the most simple. It's straightforward, right? Why make this problem harder than it needs to be? If this works, and it worked pretty well for this case, then go with that. Is it the only technique you ultimately want to have when we have an operational capability to prevent the planet? Potentially not. Potentially you should be demonstrating other technologies. But really, this was done because we get to talk about DART to all sorts of audiences. It's not usually in as beautiful a space as this, but trust me, like everybody gets this from, grade school kids all the way up. It's pretty straightforward, like ram a spacecraft into things. It had been shown from models that it would work. It had been shown sort of from lab experiments that it would work, and the thing that was remaining was this in-flight test of the technology to demonstrate it. And that's why DART, because it was the most mature, this kinetic impactor, did go forward. As far as how it wound up at NASA and ESA and collaborations, I think I'll just say that the international collaboration on this mission and the continued collaboration going forward is just such a key part of planetary defense. And I hope that we're laying the groundworks to enable that going forward.
Here? One more here.
Thank you very much. I was wondering, keeping in mind that, of course, the bigger rocks are the more dangerous ones, and you have described that the ejector provides roughly 2/3 of the momentum. What do we need to know about the composition of the rocks? Not only their position, their trajectory, and is it different in which spot we were going to hit them?
Yeah, those are all good questions. Fundamentally, the truth is that if you did have a threat to the Earth, you'd want to know as much information about it as you possibly could, right, including composition. Size is usually a big unknown with these telescopes, so in many ways, and that's how much mass is coming at the planet. So in a lot of ways, that drives a lot of the initial information that you want to have. This was an S-type object. It's like an ordinary type chondrite. Very common, the most common type of material that hits the planet, actually. And so that made it very appropriate for planetary defense, but we know from meteorites that there are a bunch of different compositions there. We know from telescopes that have looked at asteroids that they have differences, and that might change how this reacted on those different types. It's good we've taken this first step and that it's a start. How similar, how different, how important are these other things would be factors to take into account as we progress and get more accomplishments on this path.
Okay. I think that's about it. Oh, here. Okay, Alex.
Hi. So I'm wondering about the tail of Dimorphos. You mentioned that, or as we just heard, the ejector contributes a large part to the momentum. But you mentioned the tail was still ongoing for a long time. On the other hand, we don't see a change in the orbital period after the change. So how do the two fit together?
Yeah, and I think that we'll have some great people who are presenting this from the team. There's been a lot of detailed modeling about this evolution of the ejector, right? And by now, things are kind of slowly going out with the system, and it really depends on the particle size and the double asteroid system actually complicates that as well when things are gravitationally in the system and when they eventually come out from there. And so that's part of the complexity that you're seeing with there. But the majority of the stuff was done immediately right with there. That's why the period change is very stable. But the ejecta is continuing to evolve in this system, and that's more what you're seeing with the ongoing evolution of the tail. Interesting, not just for here, but for science, for active asteroids and things like that as well. But definitely, if you're at the conference, then you'll be able to see a lot more detailed modeling and things like that going forward. And that's like exactly where the team is at, we're still getting this data, still doing that, but now is when all the modeling is kicking in to really fully understand it.
Right. I have a short question myself. I'll come to you in a second. What do we know about the rotation of Dimorphos? Is it a synchronous rotation? Has it changed, or are the data not good enough to know?
Yeah, so people thought that Dimorphos would be tidally locked to Didymos because it's so much smaller and goes around, but the telescopic data have always been, haven't been, had that fidelity in order to distinguish that or not. Coming in, recapping the data that we have, DART, bam, that didn't tell you. LiCube just flew on by, right? And now we have these telescopic observations, and people are getting that data over the last 6 months, and we're hopeful that maybe teasing those out, and that's analysis that's ongoing. Actually, the end of April is when that final data set's going to be there. Maybe there'll be some other effects that they can get out of that data set. The team is working on that actively right now. But we're very excited about Hera, because Hera isn't just going to fly by, Hera's going to stay. And they're going to do these extended observations while they're there in orbit, and that's going to tell us a lot.
But we don't know anything before or after the change.
People will look back at the before data as well, right? I mean, so the telescopic data, there's a lot of data sort of from September or whatever. People will tease everything they possibly can out of that. The dynamicists are running all sorts of models. And so it's still a busy time for the team. A lot of times people are like, oh, DART, isn't that all over? You're like all done now. And I'm like, oh no, we're still very busy here analyzing a lot of data.
And then we have one last question here. Yes.
Good afternoon. My question is not a scientific question, but it is, are there actual plans to land on such an asteroid, or is it too much science fiction?
So Hera's going to land. Why don't we go over to Hera? So that's kind of their plan to do that. There's two different parts: to investigate the asteroids, to study them scientifically, that sort of thing. Obviously a kinetic impactor and a lander are not super compatible, so you kind of have to pick one or the other at the end of the day. But yeah, Hera's got plans, so maybe we should move on to Hera.
One short comment to that question. 2 asteroids have already been visited by spacecraft that brought samples back to the Earth. So they landed there and actually already brought samples back. So one is still on the way, the other one just came back. So.
They didn't land, though.
Well, they grabbed samples from. So.
But the first spacecraft to land on one was the NEAR mission, which was also built at APL, which we're very proud of, which might have laid the groundwork for doing DART today.
Which is still sitting there at that asteroid. Okay, thank you, Nancy. So the final presentation will be a look into the future by Michael Küppers from the European Space Agency, who is going to tell us what the Hera mission is going to do.
Thanks for the invitation and thanks for the nice lead over to Hera. So I'm going to talk about the international cooperation, about the Hera mission that's coming after us, and I'm trying to tell you how fascinating it's to come afterwards. I also realize it's the 5th presentation in this row, and also I realize everything I say reduces time from the cocktail, so I try to be concise. As already shown by Lindsay, we now have the DART mission having impacted on Dimorphos, and then afterwards, and with Ligia Cube flying by and seeing the immediate outcome, seeing the ejector, and after a few years, we'll have the Hera spacecraft also with its 2 CubeSats for rendezvous in the Didymos system. So what's the added value? One is, as already described just by Nancy, we have seen the deflection. We have seen that it was a bigger effect than in most estimates. And assuming a mass for Dimorphos, we also know the enhancement of the afflection. With Hera, we will actually measure the mass and get the affection this way. And just to shortly summarize also, DART has given the state before the impact, and Hera will provide us with the state of Dimorphos and Didymos after the impact. We have seen this already. This shows the effect of the impact for the case of no ejector, of some ejector, and of many ejector. And the effect of essentially the reaction force of the ejector doesn't transfers additional momentum to the asteroid in addition to the direct impact of the spacecraft. And so to understand how efficient the impact is, this needs to be considered. This is a little bit how it goes, as it will. So essentially the change of the momentum of the mass times velocity of the asteroid is the momentum of the incoming DART spacecraft that disappears at impact, plus the momentum through the impact through the reaction force of the ejector. And as this appears later in this talk, we parameterize this with a parameter beta. Essentially, if beta is 1, there's only the direct impact. If beta is 2, the effect of the momentum from the ejector would be the same as the direct impact. And to determine beta, we need the mass of Dimorphos in addition to the known quantities of the velocity change and the momentum of the incoming spacecraft. So that's the first measurement that Hera is going to do. It's supposed to measure the mass of Dimorphos, and it's done essentially by seeing the wobble of Didymos through the presence of the moon. It's a similar effect as we have for the Earth and the moon that rotate around their common center of mass and not exactly the moon rotating of the Earth. And similar, we expect a wobble of order of 10 meters of the roughly 800 meter Didymos due to the presence of Dimorphos, and this is going to be measured by the Hera spacecraft. together with some supporting measurements which essentially measure the deflection by the spacecraft through the asteroid, but that's more difficult for Hera than for other planetary missions because the mass of, or the gravity of Didymos is so much dominating in the system. The next one we already also touched upon. We know very well the change in the orbital period by Dimorphos around Didymos due to the presence of due to the impact. But there are several secondary effects that could take place, like forced librations. We see here a little bit the librations of the moon around its bound rotation of the Earth. And on the right-hand side, unfortunately, the video didn't start. It shows a model what could have happened for Dimorphos after the impact with Didymos. So, and those secondary effects, it will be tried to get some of them from the Earth, but they can be determined more accurately with the spacecraft orbiting the system. Thanks. Thanks for starting the video. It shows a model of how the wobble motion of Dimorphos could possibly evaluate after the impact, and in this case, it's an amplitude of a few degrees maximum. But this is highly model dependent, and many solutions are possible here. I'm not able anymore to switch slides. Thanks. The third measurement is slightly modified now after the impact. We always said we want to investigate the crater. Now I would say we want to see if there is a crater or if the impact was so large that it has essentially changed the global shape of Dimorphos. Here are some models for different conditions. I won't go into detail, and one can say in some cases we indeed, so in this model originally the asteroid was approximated by a sphere. In some cases you just have a crater on top of it, dart is coming from the top. In some cases you have more a change in the shape of the asteroid. You can maybe see it best in those images where you have the original asteroid. The yellow part is the part where the surface has been resurfaced, and you can see a big deviation from the original shape. So we don't currently know if we have a classical crater or if the impact was so strong, or better said, Dimorphos was so weak that we really have a global change of the body. This is something else that we will observe with the Hera mission. And finally, the overall planetary defense goal is to be able to apply the results from Didymos to other asteroids. And to be able to do this and to scale this, we need to know the physical properties of the asteroid. As an example, I have here shown models of the dependence of the moment enhancement factor, of this beta factor on porosity. And essentially, there the outcome is that we expect for large porosity a much smaller effect than for low porosity, basically because for a highly porous object, most of the incoming energy will go into compression of the target and not so much into creating ejecta. But of course, there are many factors going in, and we really need to measure these difficult physical quantities to understand how such an impact would work on a different asteroid. So this is the Hera mission itself. It will be launched in October 24, so in a year and a half from now. It will take it a bit more than 2 years to arrive end of 26, early 27. And it will start to orbit, not strictly orbit, but to stay in the environment of Didymos, basically based on the experience as the European Space Agency we have from Rosetta. So we have global characterization trajectories at a distance of 20, 30 kilometers, and then go closer and closer until at the end we hope to get in an experimental phase flybys down to a distance of about 1 kilometer. And this came in a question. The plan is for the end of the mission to land the two CubeSats on Dimorphos and to possibly land the main spacecraft on Didymos. And Hera, for the first time, takes two CubeSats called Juventas and Milani, who will autonomously operate in the asteroid system, which is also a first. This is a Hera spacecraft. You probably note at this point my different background from Lena's background. For me, a spacecraft is mostly a box with 2 solar panels and a big antenna. But the Hera spacecraft is currently being built. The integration is foreseen to complete it this year, and after testing, the launch will be in October next year. It's a medium-sized spacecraft with a mass of 1.2 tons. It's also about the size of DART, roughly 2 times 2 times 2 meters, and it's a big international collaboration with participation of 18 members of the European Space Agency plus Japan, who contribute the thermal infrared imager on the mission. That's the instrumentation. I go quickly to that. So we have the cameras, which are used for both for navigation and for science. We have a snapshot imager to get the spectral response in the visual and near infrared for some composition information. We have the thermal infrared imager, which measures the thermal properties and derived from this some surface properties, also microscopic surface properties. And we have a laser that assists in distance measurements and therefore in the shape reconstructions and also in understanding surface properties from the exact roughness distribution of the asteroid. And we have the two CubeSats, with the star maybe being the radar, the first radar as a planet on the Juventus CubeSat, plus a gravimeter for an exact gravity measurement after landing on Dimorphos, and the Milani CubeSat with a visible near-infrared imager, again for composition analysis, and also to see if there is a crater, to really see fresh material in the crater that should correspond to the meteorite that corresponds to Dimorphos, and a dust detector. This is the Juventus CubeSat illustrated, which is radar, and both the Juventus and the Milani CubeSat are also supposed to land at the end. Again, this is an illustration of the second CubeSat. Can you switch the slide? This is another presentation of Hera and of its payload.
The incredible adventures of the Hera mission. Imagine you're going on a 2-year journey with no map. And once you arrive, you must conduct cutting-edge science using only what you have in your bag. That's exactly what Hera, ESA's asteroid detective, is going to do. To carry out her mission, she's packed with more gadgets than James Bond. Hera's target is the double asteroid Didymos, and in particular its small moon Dimorphos. The pair are 181 million kilometers away, but each measures just a few hundred meters across. To find Didymos, Hera will use an advanced camera to constantly scan the skies, looking for a single dot moving more than the others against the background of stars. Bingo! The same navigation camera will then be used for science, joining other high-tech kit, including a laser altimeter and thermal camera, mapping Dimorphos' shape, and discovering what it is made of. As it moves closer and closer to Dimorphos, Hera will be largely autonomous, like a self-driving car, tracking down a crater made by NASA's DART mission. Hera has 2 intrepid assistants, also packed with new tech, mini satellites Juventus and Milani. During the journey, they will be carried inside their mothership, connected via a unique umbilical system. Once separated, Juventus will use the smallest radar ever flown into space to probe beneath an asteroid's surface for the first time. And Milani will collect tiny dust particles suspended around Dimorphos. Studying these is important to give insight into what asteroids are made from and tell us more about conditions around them. The mini-satellites will also be trialling an inter-satellite communications link, exchanging information with Hera, who will act as a data relay to keep all three in touch with Earth. This link also tracks how far away the CubeSats are from Hera, which can reveal the gravity field of Dimorphos in unprecedented detail. Clever. Testing these new technologies requires enormous ingenuity and results in more science for less money, giving the best bang for your buck. Or euro.
Okay, finally, in the last few minutes, while Hera is predominantly as a start planetary defense mission, just to point out that with the same measurements we do for planetary defense, there's also a lot of asteroid science that can be done. And the three items I'm quickly going to talk about is, one is Dimorphos is the smallest asteroid that we have visited with the spacecraft so far and investigated in situ. It's also the first rendezvous mission with a binary asteroid. And finally, we'll have the first radar investigation of an asteroid. About the first point, why small is interesting. Essentially, larger asteroids, and pretty much all asteroids larger than Dimorphos, are held together by their gravity. And of course, the smaller they become, the smaller becomes the gravity, and then the material strength that essentially glues it together becomes more important. So this is illustrated here by the I'm sorry, this doesn't show correctly. Okay, what this graph shows is the rotation speed, is the spin rate versus asteroid size, and the faster ones are to the top and the small ones are to the left, and essentially those of size Dimorphos and smaller can spin up faster because they are stronger and they are held together by their strength. While for the others, it's essentially the equilibrium between gravity and centrifugal force that limits the spin period. And I should maybe mention from the measurements we have from other asteroids and also what we can derive from the dart impact is the actual strength of those asteroids asteroids and comets is extremely low. For example, on comet Churyumov of Gerasimenko that was visited by Rosetta, some of the landscapes look so Earth-like because both gravity and strength are extremely low, so their ratio is again at the same order as on Earth. And now, for the extremely small case, where we're in this transition range, we will for the first time be able to understand the geophysics of an asteroid in the science range. And for illustration, on the right-hand side, you see Ryugu with the biggest boulder on it, which is about the size of Dimorphos. Then it's the first detailed investigation of a binary asteroid, and actually about 15% of all near-Earth asteroids are binaries. And a leading theory is that they develop due to the fast rotation of the primary, which is quite suggestive in this case because Didymos rotates in a little bit more than 2 hours. So in this case, it may be that both of those asteroids are so-called rubble piles, essentially that are just things that are held together again by gravity, that are things that have been created from collisions and reaccumulation of the fragments. And this will also be investigated with the Hera mission. And it's also not only about asteroid formation, it really helps us to understand the collisional evolution of the solar system. And it also helps us maybe to understand formation processes when the asteroids formed essentially the asteroids or the planetesimals formed from dust. And finally, the way we reach part of this is with the radar. We have the CubeSat, or the CubeSat Juventus. The radar will tell us the interior structure, and there also if the objects are those kinds of rubble piles or if they are more monolithic. and also generally how they are made of, what is the level of heterogeneity, or are they homogeneous in the interior. So, and finally, we will also get the important information about the mechanical properties from the landing of the two CubeSats on the surface, and the response to this is really much different than on a bigger object. We can see on the bottom a simulation of a lander, of the mascot lander bouncing on the Hayabusa 2 during the Hayabusa 2 mission, which actually indeed happened at the end. And those processes take much longer time, and the details of it very much depend on the mechanical properties of the material in these extreme environments. Okay, so to conclude, for planetary defense, international cooperation is important. It's an international issue, and I think we have here the first example of an actual planetary defense mission with first NASA and DART, where NASA now successfully deflected asteroid Didymos, and the follow-up will be Hera's DART mission to look at the asteroid after the impact. Thanks for your attention. Vielen Dank für die Aufmerksamkeit.
So, any questions for Michael? Yes, okay.
Thanks for the presentation. I have a question. At the beginning of the mission design, why you decide to launch the Hera after the impact rather than before the impact? I think, for my own opinion, I think if you launch, you run towards the asteroid before the impact, so we can see the characteristic of the asteroid and monitor the process of impacting, and it's maybe help for the calculation of the momentum transfer factors.
Yeah, originally there was a mission called AIM foreseen, which actually had foreseen to arrive at Didymos before the DART impact and stay during and after the impact. So this mission was proposed in 2015, 2016, and in ESA's ministerial conference 2016 did not receive sufficient funds. But there was considerable interest, and then the study was continued under the name of Hera and was then approved on the ministerial conference in 2019. But by then it was too late to arrive at the time Hera is there, and so the mission will now be launched next year and arrive 2 years later. Now, it's not such a big difference in the sense that on an asteroid not that much changes in 2 years or in 4 years. So still, we can still see the outcome of the impact. What we do not see, of course, is the ejecta from the impact, but that, again, luckily was at least partially compensated due to the presence of Lichia cube during the DART impact.
Okay, thank you. Do we have any further questions? I guess everybody is thirsty. Okay, then we thank Michael again for the talk. And we're now coming to the informal part of this afternoon symposium. The Austrian Academy of Sciences, with support by the Austrian Space Forum, will invite you to a reception downstairs, some, as we call them, euphemistically, refreshments. And I would like to thank first all the speakers for great talks. I would like to thank the Academy, especially Academy staff, in particular Victor Bruckmann here, for the organization, our technical staff for excellent support, our event staff, our communication staff, and so on and so forth, for all the assistance. And I would like to thank all of you for coming on a wet Sunday afternoon into, I think, a relatively nice and warm hall here. Enjoy the rest of your Sunday. And for those of you who are here for the week, enjoy the conference and enjoy Vienna. Thank you.